What if light suddenly doubled its speed overnight? The immediate meaning is simple. Many clocks and atomic scales would retune. Picture a city at dusk, streetlights seeming to flicker a fraction earlier. Light's speed in vacuum, called c, sets the tempo for physics across scales. This matters because changing c changes how signals and energy propagate everywhere. The rules that set atomic sizes would shift and clock rates would change. That would ripple up to instruments and daily technologies quickly. So the simple picture is this: change the ruler and measured reality moves with it. A laser pulse crossing an empty lab hall is a tiny clock. The speed of light c is that clock's rate in vacuum. It matters deeply because c appears in the equations that define space and time. Changing c rescales energy through E equals mc squared, and it changes how electromagnetic fields behave. Practically, atomic transition times depend on light travel times inside atoms, and so do spectral lines. For example, doubling c alters those spectral spacings by a clear factor. So c is not just speed, it's a universal conversion factor that sets rulers and clocks. Visualize physics as stacked shells of processes ticking at different rates. The spacing between those shells depends on how fast light carries information. That spacing matters because signal delays set rates for chemistry, heat transport, and radiation. When c changes, the separation between those layers compresses or stretches and timings reconfigure. Mechanically, reaction rates and radiative cooling scale with light travel time across those layers. A concrete example is stellar photon diffusion, which sets parts of stellar lifetimes and depends inversely on c, so changing c pushes internal astrophysical clocks, and that shifts how structures evolve over time. Out in the cosmic web, filaments stitch galaxies across vast distance. The speed of light sets how fast information travels along those filaments. That matters because observed redshift maps distance to time in cosmology. If c changed, that mapping would distort and inferred ages would shift. Mechanically, observed spectra would show shifted redshifts, making distant events appear compressed in time. For example, light from a galaxy 10 billion light-years away would sample a different epoch under a new c, so the web's history and our cosmic timeline respond directly to light speed. Now picture an observatory full of clocks and lasers, instruments humming, and engineers blinking. Instruments use c as a calibration backbone, and they assume it never changes. That matters because navigation, communications, and metrology systems rely on those assumptions. Changing c would create timing offsets in atomic clocks and phase shifts in telecom systems. For example, GPS position errors would grow from meters to kilometers until constants are updated. So engineers would be the first to notice, and their measurements would quantify how the universe had retuned. A different c reaches down and tweaks electromagnetic interactions. Molecular bond energies partially depend on electromagnetic coupling, which uses c in its formulation. That matters enormously because enzymes and proteins rely on precise bond energies. Mechanically, a changed c alters barrier heights, reaction cross-sections, and radiative transitions. For example, a 20% change in effective bond energies would dramatically disrupt protein folding and metabolism. So biology would still be chemistry, but the balance of life-friendly reactions could shift substantially. Einstein's equations link mass energy and spacetime using c as a conversion factor. That link matters because event horizons and gravitational wave speeds reference c. Changing c alters how mass curves spacetime and how fast disturbances travel. Mechanically, orbital periods and black hole radii would shift according to the new conversion. For example, binary pulsar timing would show altered orbital decay measurable with existing telescopes. So gravity would announce a changed c through mismatches between predicted and observed motions. What would people actually notice in daily life and when? Many systems depend on synchronized timing, and small drifts cascade into failures. That matters because power grids, communications, and financial timestamps require precise clocks. Mechanically, routers and oscillators would accrue phase offsets, and grid phasor measurements would misalign. For example, grid protections could trip erroneously, causing blackouts until control parameters update. So cities would experience subtle latency shifts first, and then larger systemic effects as calibration patches spread. If c changed measurably, the response would be methodical, not panicked. Scientists would quantify discrepancies, and engineers would update calibration constants. That matters because accurate measurement frameworks let technology converge on a new baseline. Practically, GPS ephemerides, atomic clock definitions, and communication protocols could be recalibrated within weeks to months. For example, updating timing references across satellites and labs would restore many services rapidly. So while the physics would be different, our instruments and teams could adapt to the new reality.